Hi guys, today we're going to do 5-7b. We're going to continue on with our inverse trig integration. Before we start doing some integrals, we do need to review a concept from back in algebra, whether it was back in your regular algebra 3-4, your 3-4 honors, but it's called completing the square. So hopefully you remember it as we start going through it. It might have been a while for some of you, but it's a method of solving quadratic equations. For example, if I give you an x squared plus 6x plus 7, and you set it equal to 0 and you're looking to get an x equals, or you're looking to solve it. If you try to factor, what numbers multiply to 7 that add to 6? Well, there are none, right? So this is not factorable. So if a quadratic equation is not factorable, there is a couple different ways you can solve it. One, you could do quadratic formula, or two, you could do what's called completing the square. Okay? We're going to do completing the square today. And if you remember the steps for completing the square, the first thing you need to do is you need to move this regular number over to the other side. So on this left side, I'm going to have an x squared plus 6x equal to negative 7. And I'm going to leave a little space there because I'm going to do something with that space here in a second. Okay? The next step for completing the square is you're going to take the coefficient in front of x. So in this case, you're going to take the 6. You're going to divide it by 2. So what's 6 divided by 2? 3, right? And then you're going to take that 3 and you're going to square it. So what is 3 squared? 9. And you're going to add this 9 to both sides of your equation in order to keep it balanced. Okay, so one more time. We took the number in front of x, the 6. We divided it by 2, and then we squared it. 6 divided by 2 is 3. 3 squared is 9. So now if you look at this left side, this turns now into a factorable quadratic. What numbers multiply to 9 that when you add them together you get 6? You end up getting x plus 3 times x plus 3. So instead of writing it twice, can I just write it x plus 3 squared? On this side, I end up getting a positive 2 when I combine my negative 7 and my positive 9. And then if I were to solve this, I could square root both sides, get the 3 away by subtracting, and then that would be my final answer, right? So I could square root both sides and get x plus 3 is equal to, when I square root 2, I get plus or minus rad 2. Anytime you square root, make sure you add your plus or minus, and then subtract 3 from both sides, giving me a negative 3 plus or minus rad 2. If you did quadratic formula, you would get the same exact answer. You would just have to reduce, but it should end up looking just like this. Okay? What we're going to do today is we're going to use it with integration. We're going to stop at this point, and we're going to write it like this. X plus 3 squared minus 2. Okay? So how is that going to help us when we do our trig integration? Well, imagine that this was over 1. Imagine that this was maybe underneath a square root. Now, what does that kind of look like if I'm trying to integrate it? Doesn't that kind of look like a inverse trig something or other? This being u, this being a, maybe a secant, an arcsecant. Okay, close enough anyway. We have to manipulate it a little bit more. But so this is how we're going to use completing the square to do trig integration. Let's try it. Here's example number 1. I'd like you to integrate dx over x squared minus 4x plus 7. What I would always do is I would always try to do regular u substitution first to see if that would work. So if I did regular u substitution, I would call u x squared minus 4x plus 7, which means du would be 2x minus 4 dx. That's way too much extra stuff, right? So that's not going to quite work. But that bottom looks really weird. First of all, it has 3 terms to it, so it's not going to be able to be a u squared minus an a squared, or a u squared plus an a squared, because there's not 2 terms, there's 3 terms. So how can we manipulate this bottom so that it'll look like what we need it to look like? Well, it's a quadratic. So let's use our completing the square and see if we can manipulate this bottom to look a little bit different. If I'm doing completing the square, I have an x squared minus 4x. If I bring it over to the other side, that's a negative 7, right? If I take the number in front of x, that's the negative 4, and I divide it by 2. Negative 4 divided by 2 is negative 2. What's negative 2 squared? Positive 4. add that to both sides. Okay, this is a factorable quadratic. What numbers multiply to 4 that when you add them together you get -4? Isn't that -2 and -2? Or can I say x minus 2 squared? Over on this side I get a what? -3? All right. Instead of having that -3 over on that opposite side, can I move him over next to this x minus 2 squared and have it look like that? Getting rid of this equal to 0, so just looking at one side of my equation. Could I take this problem now, this x squared minus 4x plus 7, doesn't that actually turn into 1 over x minus 2 squared plus 3 dx? Doesn't that look a little bit closer to what I need? 2 terms on the bottom. Okay, so using or completing the square to break down the bottom so that there's 2 terms. If there are the 2 terms, then we need to figure out what we're going to call our a, what we're going to call our u, and so on. There is no radical here, so this bottom is going to be, or it looks more like a tangent, arctangent, doesn't it? If I'm doing arctangent, then let's call this one u. That would mean that I would need this to be an a. So if I need this to be an a squared, if I need this to be an a squared, if I need 3 to be an a squared, then what would a have to be? Square root of 3, right? So that works. So a squared would be 3. Perfect. So then u squared, or excuse me, u would be x minus 2. If u is x minus 2, then that means du is going to be 1 dx, which is also perfect because that's what I have here on the top. So let's use our u substitutions, and I get 1 over u squared plus my a squared du. And what is the integral of 1 over u squared plus a squared? Isn't that my arctangent? All right. Using your formula for arctangent, it's 1 over a, which in this case was rad 3. Arctan of u, which is x minus 2 over a, which is rad 3, plus c. Good? Just a little manipulation, a little algebra manipulation. Let's try another one. All right, find the area of the region bounded by the graph of f of x. And so f of x is 1 over the square root of 3x minus x squared. And the x-axis and the line x equals 3/2 and x equals 9/4. So now we're finding the area underneath the graph. So what's another name for finding the area underneath the graph? What are we doing here? What are they asking us to do? Are they asking us to integrate it? Right? They're asking us to integrate this function, find the area underneath, from where to where? From x equals 3/2 to 9/4. So really we're just doing this. Okay? All right. If I try to do my regular u substitutions and I call u 3x minus x squared, that means du is going to be 3 minus 2x. That's way too much extra stuff, right? Okay. On the bottom here, I have 2 terms. But these 2 terms look a little bit different. They're not just a constant and then a number. So if I called u, or if I called u x, I can't call a 3x because a is supposed to be just a constant, no variable. So this looks a little bit different. So let's see if we can manipulate this bottom a little bit. I'm going to write it over on the side, and I'm actually going to write it a little bit out of order, just because I like to see my x squared in the front. So is that okay? Instead of a 3x minus x squared, can I call it a negative x squared plus 3x? Okay. I also like to see that this x squared is positive. So could I GCF out a negative? Do something like that? Okay. And then let's algebra manipulate, and let's do a little bit of completing the square. So if I complete the square with the stuff inside, I have an x squared, a minus 3x. What is negative 3 divided by 2? Just negative 3 halves. What's negative 3 halves squared? Negative 3 halves squared is a positive 9/4. So I have a positive 9/4 there. And then I also have a 9/4 here. Okay? All right, here's the tricky part though. Because there's this extra negative out in front, there needs to be a negative on this side to balance out that 9/4. Okay, because this isn't a normal completing the square on this left side because of that negative. So because there's that negative there, we also have to add a negative to the right side. Okay? All right, if I were to go to finish this completing the square, I would have an x. What number is multiplied to 9/4 that when I add them together I get negative 3? What you end up getting is negative 3 halves, which is the same always as when you divided this number by 2. Okay? So when you're trying to factor that perfect square inside here, it's always going to be whatever that middle term is divided by 2, so 3 halves. So 3 halves times 3 halves is 9/4. 3 halves plus 3 halves is 6 halves, which is 3, right? Okay, on this side I have my negative 9/4. Could I actually bring him over? I'm going to bring him over to the same side and make him a positive 9/4. Okay? And since I need this to look more like one of my trig inverses, and I want this negative to be in between, could I rearrange this back to its original form where the 9/4 is in the front minus an x minus 3 halves squared? Okay, I just rearranged it in a different order. So now I'm going to take this and I'm going to rewrite my original problem. Okay, so my original problem is the integral from 3 halves to 9/4 of 1 over the square root. The square root's still there. Remember, the square root's still there, but we just manipulated underneath. When we manipulated that underneath, we broke it down into 9/4 minus x minus 3 halves squared dx. Woo! I haven't even started integrating. All right. So now, what would we have to call u? We would have to call u this x minus 3 halves, which means we would have to call something over here a. Well, doesn't that work now? Because now a is a constant, it's just a number. This is perfect. Okay, so if we call u x minus 3 halves, then that means du would be what? 1 dx, which is good because that's what we have on the top. And then what would a have to be so that a squared is what? 9/4? What would a have to be so that a squared is really 9/4? Wouldn't a really then have to be 3 halves? That works, doesn't it? Because if I square it, I get 9/4. Okay. So, rewriting again. I've got an integral from 3 halves to 9/4 of 1 over a squared, which is 9/4, minus u squared du. What is the integral of 1 over the square root of a squared minus u squared? Can you do it without looking? It's an arc sine, isn't it? Okay, so I have arc sine, or sine inverse, of u, which was, what was it? X minus 3 halves, over a, which is 3 halves. But this time, instead of plus c, don't we have a limits of integration? We have it from 3 halves to 9/4. Okay. So if I have a definite integral, can we plug in and evaluate? Using our fundamental theorem of calculus, can I plug in my 9/4 here minus 3 halves over another 3 halves? I know that looks funny. We'll change it here in a second. Minus my sine inverse of 3 halves minus 3 halves over another 3 halves. Do that. All right. Let's see here. Okay. All right. When I'm doing this, I need, looks like I need here a common denominator. So can I change this to a 4, which means this is a 6/4? So on the top here, I get sine inverse of 9/4 minus 6/4 is 3/4 divided by 3/2, aka multiply by the reciprocal, 2/3. So then really what do I get here? Sine inverse of 1/2. And we'll do that here in a second. Let's finish up this other side. 3/2 minus 3/2, that's a 0. What's 0 divided by 3/2? 0. So sine inverse of 0. All right. So I have sine inverse of 1/2 minus sine inverse of 0. So using our unit circle, we need to figure out where sine equals 1/2. Make sure that you're doing it in the correct quadrant. You should get pi over 6 minus, where does sine equal 0? Make sure you're doing it in the right quadrant. You should get sine of 0 is at 0. So what is pi over 6 minus 0? Whew, just pi over 6. That means the area underneath the curve of that function from x equals 3/2 to x equals 9/4 is pi divided by 6. Okay? Lots of manipulation, trying to get it the way you need in order to integrate it. The more you practice, the easier it'll become. Your homework is 5-7B, page 385, numbers 31 through 42 all. 31 through